Hi everyone, it's a pleasure to introduce our guest speaker today, William D. Phillips. Uh, Professor William Phillips is a brilliant physicist who work helping us slow down and cool atoms using light, opening new door in quantum physics. We're working at the National Institute of Standard and Technology. He developed a groundbreaking technique to cool and trap atoms. For this achievement, he received the Nobel Prize in Physics in 1997 alongside Steve Cho and Claude Cohen-Technology. Today, he continues to teach and inspire students as a professor at the University of Maryland and remain as a strong support of science education. Please join me and warmly welcoming Nobel laureate and pioneer in atomic physics, Professor William Phillips. Professor Phillips, thank you so much for being here with us today.
Here, I'm happy that I can join you in this remote way and to talk to you about the quantum reform of the modern metric system.
So you can start. You can make sure your presentation in screen.
Okay, now do I need to start that or?
Okay.
Okay, I'm not sure where we are now. Okay, so let's go through the process of starting the presentation again. Okay.
Okay, I can see it.
Okay, good. Okay, excellent. So the title of my presentation is a new measure, the revolutionary quantum reform of the modern metric system. And as you've seen, I'm part of the Joint Quantum Institute, which is a joint operation between the National Institute of Standards and Technology and the University of Maryland. And at the NIST, I'm a member of the Laser Cooling and Trapping Group, which is led by Ian Spielman. And these people are the people I work with on a daily basis, and it's a great pleasure to be associated with such fine scientists. I'm also representing the International Union of Pure and Applied Physics. This is an international organization of countries that act internationally in order to promote physics. And one of the things historically that IUPAP has done is to promote the adoption of the modern metric system, what is called the International System of Units, or the Système International d'Unité, the SI. And IUPAP was one of the major forces in getting that system, the system we all use today, adopted. And as a member of the Commission on Units and standards, I'm spreading the word about the latest revision and reform of that system. So one of the things I want to encourage you to do is to think of questions. I'm going to stop several times during this presentation to take your questions. And my understanding is that you should put these questions into the chat function if you're watching on YouTube. But Mustafa, would you like to give some more details about how the audience members should communicate their questions to you?
Yeah, sure, of course.
So is there anything in particular that the audience members should know about how to enter their questions?
Okay. I have some questions, but I think after the presentation, we can show all of questions.
Well, I'm hoping to stop
Yeah,
several times during the presentation to
yeah, of
get
course.
questions. Okay. Well, let's continue then. One of the things that informs the context of this talk is that last year, 2025, was the UNESCO International Year of Quantum Science and Technology. And the reforms of the metric system that I'm going to talk to you about are particularly quantum. And so I think that it's appropriate that we discuss this at a time that we've just been recognizing the International Year of Quantum Science and Technology. So again, a new measure, the revolutionary quantum reform of the modern metric system. Well, the metric system, as we know it today, began in the context of the French Revolution at the end of the 18th century. So the metric system is really old. And what I'm claiming is that the recent reform that we've had of the metric system is the biggest revolution that we've had in the metric system since the French Revolution itself. And in fact, on the 20th of May, 2019, not too long ago, in the whole sweep of history of metrology, we had what I claim is the greatest revolution in measurement since the French Revolution. And the nature of that revolution is a fundamental change to the International System of Units, what the official name of the modern metric system. This system expresses all physical quantities in terms of 7 base units: the kilogram, the meter, the second, the ampere, the kelvin, the mole, and the candela. Everything that we measure in the metric system is some combination of one or more of these base units. And the nature of the reform that has happened is that today all of the base units of the International System of Units are now defined by fixing the values of constants of nature. Now, in order to see how this can be done, we're going to consider an example of an earlier unit of measure, and namely the unit of time, and review how the unit of time has evolved over time. And with apologies to the late great Stephen Hawking, I'm going to bring you my version of a brief history of time. Well, ever since we have had seconds as a unit of time, the second has been thought of as being a certain fraction of a day. And that fraction is 1 over 24 hours in a day, times 60, 60 minutes in an hour, times 60, 60 seconds in a minute. Now, the question is, what is a day? And the definition of the day is problematic, because the length of the day, for example, the solar day, changes during the year because of the fact that the Earth's orbit around the sun is elliptical. The axis of rotation of the Earth is tilted relative to the plane of the orbit. And so the length of the day changes significantly during the course of a year. So the definition of the day is the mean solar day, that is averaged, the average value of the solar day averaged over a year. But since about the year 1900, we've known that even this average changes with time. One of the reasons is that the tides, for example, exert a frictional force on the Earth, and that frictional force slows the Earth down. When there are earthquakes, it redistributes the mass of the Earth, and that changes the moment of inertia of the Earth, and that can change the rotation speed. If ocean currents change for any number of reasons, for example, from climate change, then those ocean currents represent a contribution to the angular momentum of the Earth, and by conservation of angular momentum, the rotation of the rest of the Earth has to change. So this puts us into a difficult situation. We have clocks, and here's one example of a clock that is better than the Earth. This, in fact, is a picture of the first atomic clock, which was made at NIST, or at least at the ancestor of NIST, which was back in those days called the National Bureau of Standards, the place where I work today. In 1949, made the first atomic clock. Now, I've put the word atomic in quotation marks because, in fact, this clock used a molecule, namely the ammonia molecule, and the ticking of that ammonia molecule, the ticking frequency being the difference between two energy levels in the ammonia molecule, that formed the basis for the atomic clock. And this atomic clock is better in the sense of being more stable than the rotation of the Earth. But the definition of the second was based on the Earth. So now we are in an uncomfortable situation where we have a technology, namely atomic clocks, that can measure time better than the very definition of time, which is based on the rotation of the Earth, and the rotation of the Earth is not constant for all the reasons that we've discussed. So it was necessary to change the definition of the second because of the fact that we had a technology that could measure time better than the very definition. In 1955, this group of scientists, Perry and Essen, at the National Physical Laboratory in the United Kingdom, made the first cesium clock. And that cesium clock inspired a redefinition of the second. Now, here's how an atomic clock works, or at least here's an oversimplified version of how an atomic clock works. Here we have a cartoon of a cesium atom. There's one valence electron. There are a lot of electrons around the nucleus, in addition to the valence electron, but the valence electron is the important one. And the nucleus has a spin, as does the valence electron, and being a spinning charge, both the electron and the nucleus create a magnetic field. And if the orientation of the electron relative to the nucleus changes, that changes the energy of the atom. And that energy change is called the hyperfine energy. If I send in microwaves at a frequency of some 9 gigahertz, that is the energy needed. That is the energy of a single photon of the microwaves has the energy needed to flip the spin of a cesium molecule. And the way the atomic clock works is that you adjust the frequency of the microwaves until the spin of the electron flips, and when the frequency is just right, then the electron flips, and then you know that the frequency is this number. Effectively, what this does is it defines the frequency of the hyperfine transition. In other words, we're taking a constant of nature, the hyperfine frequency of a cesium atom, and we are defining what that frequency is. It's exactly this number. This is the way in which the second is defined today, by setting the value of the hyperfine frequency of the cesium atom. So this is, in fact, the official definition of the second since about 1967, that the second is the duration of some 9 billion periods of the radiation corresponding to the transition between the two hyperfine levels. So ever since this definition has been accepted by the international community. In fact, even before that, from the time of the first atomic clock with cesium in the UK, the quality, the uncertainty of this clock has been improving. A kind of a Moore's law, an exponential improvement until it was good to about a part in 10 to the 14th in about 1990. But at that point, the realization of the second using cesium atomic clocks, in a sense, stalled out. That is, it was difficult to make it any better because of the fact the atoms were moving so fast. At the temperatures that we need to use, a little bit above room temperature, in order to melt the cesium metal and evaporate it so that we get isolated atoms of cesium in a gas. The atoms of cesium are moving at more than 100 meters per second. And that rapid motion of the cesium atoms makes it very difficult to make measurements on them. Laser cooling, which, as you heard in the introduction, was part of the work that my group and I have done at NIST, was pursued exactly to solve this problem, to produce atoms that are going much slower than the 100 meters per second that thermal cesium atoms move at, in order to improve the performance. And in fact, it has worked. The performance of these clocks are now good to a few parts in 10 to the 16. In other words, the improvement due to laser cooling, to making the cesium atoms move more slowly, has been almost a factor of 100. So that's wonderful. The benefit of laser cooling is shown in the continuation of this exponential improvement of the performance of atomic clocks, so that today those atomic clocks are good to, as I said, a few parts in 10 to the 16. This is the best measured quantity in science, measuring the second, realizing the second to a few parts in 10 to the 16, and comparing the frequency of other transitions. These are the best measurements of any physical quantity. Here's a picture of one of those atomic clocks. That a column to the right is a vacuum system with magnetic shields around it. Cesium atoms are cooled down to about 1/1,000,000th of a degree above absolute zero, and then launched up through this tower to about 1 meter high, coming back down after about a second. And that long observation time allows the clock's creators, Don Meekhoff and Steve Jeffords, to realize the definition of the second to a few parts in 10 to the 16, the most accurately measured quantity in the International System of Units. So here is the key concept. We started with what was essentially an arbitrary artifact, the rotating Earth. There's nothing special about the Earth other than the fact that it's our home, the place where we live. There's nothing special about its rotation rate, and as we've seen, it can change for any number of reasons, like the tides and earthquakes. That rather arbitrary artifact has been replaced by a constant of nature, the frequency of a transition in the cesium atom. And I emphasize, it's a quantum transition, and that is one of the things that guarantees the constancy and the uniformity of that transition, regardless of what atom of cesium we choose to use for this purpose. These giants of physics of the 19th century had already anticipated that this might be a good idea. Kelvin, Lord Kelvin, said that atoms, ready-made in infinite numbers, are all absolutely alike in every physical property. The time of vibration of a sodium particle is known to be absolutely independent of its position in the universe. So now Kelvin wasn't exactly right about that. The vibration of things like sodium or cesium does vary because of gravitational potential, but that was something that wasn't understood until early in the 20th century with Einstein's theory of general relativity. But he was right about the fact that all the atoms are alike in every physical property. Now, this is a remarkable statement by Kelvin because it came at a time when a large number of people didn't even believe in atoms. But Kelvin guessed correctly that all atoms of the same type, that is, all cesium-133 atoms, were completely identical to all other cesium-133 atoms. And he thought that this would be the right thing to use as a standard of time rather than the Earth. And in fact, his prediction has come true in the middle of the 20th century and continues today in the beginning of the 21st century. Now, I think this is a good time at the end of my brief history of time to take a little bit of time to receive your questions. So, do we have any questions in the chat, Mustafa?
Yeah, of course. The first question by Adil Qasim about the modern definition of unit system, relate or recent and robust theoretical framework. Their experimental confirmation represents a particularly demanding methodology challenge. I think this is just a comment. If you have any comment about this one.
Well, okay. I have to say, first of all, because of the echo, I'm having a little bit of a hard time understanding exactly. But
Yeah,
I
I'm
think
so sorry.
the comment is that this is a metrological challenge, or was a metrological challenge, to determine that in fact the Earth's rotation rate was changing. It was a challenge because one needed to have some sort of an instrument that was better than the rotation of the Earth. Is that essentially what the comment is?
Exactly.
Okay. Well, so let me say a little bit about the history, because I think this is a good.
I think there is another question. Can we replace the standard units by quantum units?
Oh, I'm having a hard time. This echo is. I'll tell you what. Why don't you write? If you could write that into the chat, maybe that will work better. I can see the chat right here, and that way I'll be able to understand better. Oh, okay, fine. Right. I see. So the question is how to explain to young students about quantum theory in a simple way. Well, I'm afraid that the answer to that question is not itself very simple. I've been giving talks during the past year about quantum mechanics, and I give 1-hour talks about the creation of quantum mechanics and how it's affected not just measurement, but almost everything in our lives. So let me give a very brief answer to this. One of the key features of quantum mechanics, something that was first proposed by Louis de Broglie in 1923 and really formalized by Erwin Schrödinger in 1926, is that particles, like electrons, behave like waves, and that waves, like light and sound, behave like particles. In other words, everything, the thing that we thought of as being particles in the 19th century, like electrons, which were discovered late in the 20th centuries, or atoms for that matter, all those particles also behave like waves, and they behave like particles, and things that we understood to be waves like sound and light in the 19th century, that these phenomena also behave like particles, that everything behaves like both a particle and a wave. In quantum mechanics, this is called wave-particle duality. Now, one of the things that this wave-particle duality leads to is the Heisenberg uncertainty principle. The idea that if you want to specify where a particle is, then you will not know the momentum of the particle. That is, there will be an uncertainty in the momentum of the particle that is related to the uncertainty in the position of the particle. And this follows directly from the behavior of the particle as a wave. If there was only a single momentum to the particle, that would correspond to a wave that goes on forever. So you would have no idea where the particle was because the wave has an infinite extent. If you want to localize the particle, you have to add together lots of different wavelengths, which correspond to different momenta, in order to cancel out the waves that occur at distances that are far away from where you want to localize the particle. So that fact that you have to add many momenta together, many wavelengths together, means that you don't know what the momentum is once you start to have a better idea of what the position is. So this is the nature of Heisenberg's uncertainty principle. So these are some of the key features of quantum mechanics, that everything behaves as both a particle and a wave, that that fact means that we have this uncertainty principle that says that we cannot know both where a particle is and its momentum, that the product of the uncertainty in the momentum times the uncertainty in the position is can be no smaller than Planck's constant. And that these features have led to all sorts of amazing things. Perhaps the most consequential of the things that quantum mechanics has led to was the invention of the transistor, for which you needed to understand that electrons behaved like waves. And the transistor has completely changed our lives. That is, because of the transistor, we have things like semiconductor electronics. We have the ability to have a seminar like this, where I can speak to you from my home, and all around the world, people can be listening to it. That happens because of semiconductor electronics and because of quantum mechanics. Now, that was not a very short description of how to describe quantum theory, but if I was to give a more complete description, it would be not just hours, it would be an entire class that would take 2 semesters. Now, since we had the other question about the
Yeah, there is another question.
okay, so okay, let me read that. Okay, right. So the question is a comment about the fact that the new definition of the unit system relies on a lot of theory, and that's true. But that theory is in fact backed up by experiments. So so let me give an example of that. In the context of time, which we've been talking about right now, one of the theoretical understandings that has led us to the current definition of the second, based on the cesium atom, is the understanding, which comes from quantum mechanics, that every cesium atom must be absolutely identical to every other cesium atom of the same isotope. That is, every cesium-133 atom is identical to every other cesium-133 atom, and this gives us the confidence to make atomic clocks and to know that every place in the world where people make atomic clocks, they are getting the same ticking frequency for those atomic clocks. Now, the question is, theoretically, we know that from our understanding of quantum mechanics, but do we confirm that by experiments? And the answer is yes, that people compare in different laboratories. They build their atomic clocks, and then they compare these atomic clocks by sending radio signals to satellites so that two people in two different laboratories, separated by hundreds of kilometers, can look at the same satellite, and the satellite relays the signal from one laboratory to the other, and then they can then compare these clocks. And it is that kind of experimental comparison that tells us that, in fact, the quality of these clocks is good to a few parts in 10 to the 16, as I mentioned. That's one of the ways in which we determine how good these clocks are. So we have confirmed that different cesium clocks are, in fact, good to that level of accuracy, a few parts in 10 to the 16. As we'll see later in my talk, there are other clocks that are waiting, in a sense, to competing to change the definition of the second to something even better. And those clocks are also known to be even better and more consistent than cesium. So it's true that our understanding is based on theory, but it's backed up by experiment. So what else?
That's a new question.
Let's see. Okay, what is the essential minimum of math and physics one must master to seriously enter quantum or relativity research, even if coming from another field? Well, that's a good question. If you really want to contribute to an understanding of quantum mechanics, then it is true that you need a good bit of math. You need to know linear algebra. You need to know ordinary and partial differential equations, at the very least, because these are the foundational fields of mathematics that allow us to do quantum mechanics in what's known as the Heisenberg picture or the Schrödinger picture. That is, these two ways in which quantum mechanics was developed in around 1925-26 are equivalent to each other, but use different mathematical approaches. And you need to know both, because depending upon the problem that you're doing, you may want to use one approach or the other. So you need to know linear algebra, you need to know differential equations. Of course, you need to know calculus. That's what comes before understanding differential equations. So that's the mathematics that you need to know as a minimum. And depending upon the specific things that you study in quantum mechanics, you may need to know other branches of mathematics, like special functions, because for particular physical systems, the solutions of Schrödinger's equation, for example, involve special functions, and so you'll need to know something about those. So it does mean that it requires a good bit of study in mathematics, but mathematics is the language of science, so we should embrace it. We should think of it as being a wonderful resource rather than as a stumbling block. So, anything else?
Yeah, I think there's another question.
Okay, great. Let's go on then. So now I'd like to talk about length. And in a sense, the story of length is even better. And one of the reasons is that while time was certainly important historically, length was really important. And the reason is that the measurement of length was something that was absolutely necessary for a lot of commerce and a lot of construction. So the earliest definition of length was based on the human body. The cubit was the distance between the elbow and the end of the finger. The yard is the distance between the center of your body, your nose, and the ends of your finger. The fathom is the spread of your arms. The foot is the length of your foot. And these were the kinds of units that were used in early and ancient times. Now, the problem was that while this was extremely convenient because it meant that you were carrying your standards of length with you all the time, these standards were not consistent. If, for example, you were buying fabric from a fabric merchant, and the fabric merchant is short in stature, you might not get as much length of fabric as you had expected because the merchant is selling fabric by the fathom, for example, based on his size. Now, one solution to this problem is to standardize the units of length based not on the body of the person who's doing the measurements, but on a particular body, typically that of a king or a pharaoh as the standard. And that I mentioned the pharaoh because this is exactly what was done in ancient Egypt. The royal Egyptian cubit was based on the size of the pharaoh's forearm and his hand. And because the pharaoh was not generally available to make these measurements, they created an artifact. And there's a picture of part of that stone artifact that represented the length of the pharaoh's forearm. This was officially the royal cubit. And people who were building structures like the pyramids, for example, would calibrate a wooden standard against the stone standard, and they were required to check that calibration, to recalibrate every month, and there was a very severe penalty if they did not recalibrate. This tells us that the Egyptians were extremely serious about their metrology, and that seriousness led to really fine results. The baselines of the pyramid are consistent to a small fraction of a percent. The pyramids are square to an accuracy of 12 arc seconds. They were really good. These were excellent measurements, and it's because they took their metrology seriously. And that metrology was based on an artifact, a piece of stone that represented the standard of length, in the case of the Egyptians, the royal cubit. Well, in medieval times in Europe, similar artifacts were used all over the continent, and they would vary from town to town. And here's an example of one particular town, the city of Regensburg in Germany. And this particular tourist is comparing her fathom to the fathom of the town of Regensburg. And you can see that the Regensburg fathom is considerably larger than her fathom. So perhaps this would be a good place to buy fabric. But the difficulty would be that if you were to go to another nearby town, you would find a different standard of length. So this was a common problem, but it was a worrisome problem. And it was a problem that the French revolutionaries decided they would fix. The French revolutionaries decided that they would create a new system of measurement, what we call today the metric system. And the base of that metric system would be a new standard of length called the meter. And the meter would be defined using the Earth itself. This was in the spirit of the French Revolution, of égalité, fraternité, liberté. They wanted these measurements to be available to everyone. And since the Earth was something that was, at least in their conception, available to everyone, they made the meter to be based on the size of the Earth. And the definition of the meter was that it is 1/10,000,000th of the distance between the North Pole and the equator along a meridian that passes through Paris. So, in order to realize that that definition of the meter, they sent out astronomers and surveyors to determine what the length of the meridian was between Dunkirk in France and Barcelona in Spain. And that that process took several years, and the spirit of that was that they were going to produce a standard of length that would be good for all time and for all people, à tous les temps, à tous les peuples. And in this picture you see here of a medal that was cast to commemorate the idea of the meter, you see this mythological creature is using dividers to measure the Earth. And this is effectively what they did. They measured the Earth using astronomical and surveying tools. They measured the distance between Barcelona and Dunkirk, and then they extrapolated to the full length of the meridian. Now, this was wonderful. They had a new version in terms of the old, one of the old length standards. But the trouble is, you can't go measuring the Earth every time you want to measure how long a table is, for example. And so they did the same thing that the ancient Egyptians did. They made an artifact, and this is a picture of the artifact that they made. It's called the Meter of the Archives. It was made to be 1 meter long, based on the surveying that was done. That several years project. They made it based on that. They made a platinum rod that was 1 meter long, and they deposited it in the archives of France. So it became the standard of length for the country of France. And some decades later, the countries of the world gathered in 1875 to draft and ratify an international treaty called the Convention de Mètre, the Meter Convention, the Treaty of the Meter. And they adopted the meter as the standard of length for all of those countries. And they made a new meter bar made out of platinum iridium to be the same length as the Meter of the Archives that was deposited in the archives of France. Now, the old meter was what's called an N standard. Let me go back to it. The meter was the difference between one end of the rod and the other. The new meter is what's called a line standard. There were 2 scratches engraved into the meter that were exactly, as far as they could measure, the distance between the ends of the old meter, the Meter of the Archives. And so the definition of the meter from 1875 was that the meter was the distance between these 2 scratches. Now, there came very soon a problem. This isn't a problem. This is just to indicate that last year was the 150th anniversary of the Convention de Mètre, certainly a very important date in the history of metrology. But here's the problem. Physicists had been spending the 19th century learning about the nature of light. They'd learned that light was a wave, and they learned how to make interferometers so that they could interfere different beams of light because they're waves. And here's an example. This is a kind of a cartoon version of what's called a Michelson interferometer. You have a source of light, You send it into a beam splitter that is like a half-silvered mirror so that some of the light goes through and some of the light is reflected. So each of those beams of light, the one that's reflected and the one that's transmitted, encounters another mirror that reflects it back on itself and recombines the two beams of light so that they interfere. This is a picture of the interference pattern, and it's dark where the crest of one wave corresponds to a crest in the opposite direction of another wave. Then you get, this dark spot. And when the two crests line up, then you get a bright line. And you can change this center from being dark to bright by changing this mirror by 1/4 of a wavelength. Now, a wavelength is about a half of a micron, about a half of 1/1,000,000th of a meter. And so 1/4 of that changes this from light to dark. So it's easy to make measurements of the displacement of this mirror. That's a small fraction of a millionth of a meter. The scratches that are on this meter bar are 20 millionths of a meter wide. And we now have a technology that can measure length, or at least displacement, to better than a millionth of a meter, better than 1 micron. So now we have, once again, the problem that we had with time, with the second. We have a technology, in this case, optical interferometry, that can measure length better than the definition of length itself. The definition is the distance, that the meter is the distance between these two scratches. The scratches are 20 microns wide. How do you determine where the center of that scratch is? This is a very difficult thing, whereas it's quite easy to determine where the center of this dark spot is, or where the center of these bright lines is. It's very easy to determine where the center of that is, to much better than a millionth of a meter. So we have a technology that is better than the definition itself. That means that we need to redefine what we mean by a meter. It took a long time, until the year 1960, which, by the way, was the year that the laser was invented. And the meter was redefined as being a certain number of wavelengths of the light that comes from a krypton lamp, which is shown here. You put krypton gas in there, you put an electric current through it, it glows orange, and the wavelength of that light was used to redefine what was meant by the meter in the year 1960. Now, remember, 1960 was the year that the laser was invented. It didn't take very long before people were making lasers that put out light that was more pure than the light that came from a krypton lamp. So the krypton lamp, it turns out there are a number of different energy levels that are contributing to the light that comes out of the krypton lamp. The atoms are moving around really fast, and so their Doppler shifts shift the wavelength of the light, and none of those things happen with really good lasers. So here's a picture of a helium neon laser that can be stabilized to a transition of a molecular iodine, and this is much better than a krypton lamp. So once again, we have the uncomfortable situation where we have a technology, namely lasers, that's better than a technology for measuring length, namely lasers, that's better than the definition of length, which was based on the light from a krypton lamp. So it's obvious that, once again, we need to redefine what we mean by a meter. And the obvious choice would have been to take one of these helium neon lasers that puts out a red light, stabilized to a transition in iodine. These things were known to be good to something like a part in 10 to the 12, much better than you could measure with the krypton lamp. The obvious choice would have been to redefine the meter in terms of this iodine-stabilized helium neon laser. But fortunately, people did not make the obvious choice. They made instead a beautiful and brilliant choice. They defined the speed of light. So how does that work? How does that give you a length standard? Well, we have this universal relationship that the wavelength of light times the frequency of light is equal to the speed of light. So that means that if you were to define the speed of light, and if you could measure the frequency of that light, then you immediately know what the wavelength of the light is, and you can use that as your length standard. Now, the beauty of this is that it doesn't matter what the source of that light is. So if, for example, we make a better laser, so the light coming from it is more pure than any laser that we had before. Or if we find a new way of measuring the frequency of the light so that we can do the frequency measurement better than anyone has done before, we don't need to change the definition of the meter. The definition of the meter then and now, then being 1983, is that the meter is the distance that light travels in vacuum during a certain time interval, and that time interval is 1 over the speed of light in meters per second, by definition. This definition of the meter effectively defines the speed of light. And this is, we hope, going to be good for all time. If we make better lasers, if we make better frequency measurements, we don't need to change the definition. And these two gentlemen, Jan Hall and Ted Hench, did exactly that. They made better lasers. They developed better methods for measuring frequency. And today, these kinds of measurements, based on the things that they did, for which they were recognized with the 2005 Nobel Prize, these developments provide the very best measurements of length that are used routinely today. So now we have another key concept. We started with an artifact. We changed the definition of the meter from the artifact to a constant of nature, namely the wavelength of light coming from a certain atom, krypton. And then we changed that to a fundamental constant of nature, the speed of light. And this is the kind of reform that we're now going to apply to all of the base units of the International System of Units. Because if we do it this way, we should never need to change the definition again. So, the definition of the meter is, I claim, both brilliant and beautiful, even more beautiful than the definition of the second. And on the 20th of May, 2019, just a few years ago, the international community brought this same beauty to the definition of the kilogram and the ampere, the Kelvin, and the mole. And now I'm going to tell you why and how, but first, I'm going to stop and ask for questions. I've even suggested a few possible questions, but I think that you probably have better questions than the ones that I suggest. And of course, if you have any leftover questions about time, I'll be happy to answer those as well. Now, I see that there is a new question. I'm enjoying the talk. One question that comes to my mind is the redefinition of the unit of time. Since time units are problematic, how that can change the view we have to time. Well, okay, so this is probably more of a philosophical question than a scientific one. That is, we have many ways in which we think about time, and the people have since perhaps the beginning of recorded history asked themselves the question, what is time? Now, I like the definition that Einstein gave. Einstein said that time is what a clock measures. So if I define time using a different kind of clock, like a cesium clock, or maybe in the future a different kind of clock, then whatever that clock is, whatever that definition is, that's what time is. Now, we might also ask the question about relativity. The theory of relativity tells us that different observers will measure different times. And this, of course, is a problem. So there is underlying the definition of time, which I've shown to you in terms of the cesium transition. There is underlying that an understanding. Well, it's not just an understanding. It's made very clear that what is meant is what relativistically is called the proper time. In other words, it's the time in whatever reference frame the observer is using. And we know that different observers will measure different times. So, for example, if one observer is moving relative to another, then the one observer will measure a ticking frequency for a clock that is different from his own if the other observer is moving. And you have to make a correction for that. And we do that all the time. So these difficulties, which are real difficulties, are things that we must take into account, but we know how to do it, at least in principle, and it's in fact part of the definition that we include such relativistic differences in the measurement of time. So, okay, so we're also asked, what is the relationship between quantum mechanics and the redefinition of SI units? And the answer to that, well, there are perhaps a number of different definitions. One is that we're using quantum phenomena to make these new definitions. So, for example, with time, we're looking at a transition between two energy levels in an atom as giving us the standard of time. These are two energy levels in the current definition, are the two hyperfine levels. And the fact that there is that energy difference is a quantum mechanical phenomenon. And the fact that that energy difference is the same for every atom of the same kind, that is also a quantum mechanical phenomenon. So it's the fact that we are using quantum features, namely energy levels, and that we're relying on our understanding of quantum mechanics to guarantee that that the definition is uniform, that we don't have to worry, for example, about where the cesium came from, that quantum mechanics guarantees that all cesium atoms are the same. So the next question, do you believe that an academic environment is an essential condition for creativity in theoretical physics? Is it mathematical depth and exposure to open problems makes a difference regardless of the formal path? Well, it's a philosophical question more than a physics question, and I'm not sure that I'm wise enough to give a good answer. I think that if we look at the way in which progress has been made in physics over the years, in early times, those advances in physics were perhaps not made by people who were in universities or necessarily in universities, because universities were just beginning. Probably we should think of the beginning of physics or the beginning of science as the beginning of the scientific revolution, sort of the beginning of the Renaissance, for example. And there were universities at that time. And if I think back to the people who made some of the biggest advances, people like Galileo, people like Newton, these were people who were, at least to some degree, associated with universities, but very often they taught students on their own outside of the context of a university. So I don't think that university per se is a requirement, but I think that some kind of an intellectual environment, not necessarily that it would be associated with the university, but it would be associated with people trying to understand and doing it very often as a as a group effort. Now, some of the big examples are associated with individuals, but I think that much of the recent advances have been done by teams of people who bring to the problem different perspectives and different expertise. So, as I said, I don't think I have particular wisdom here, but I think that the key thing for making scientific advances is an intense attention to the intellectual pursuit of truth. So let's see what the next question is. By fixing these constants to exact quantum values, have we reached the end of history for measurement, or are there still things that are missing? Well, so what we're hoping is that these new definitions will be the last. I don't think we can guarantee that, and you'll see when we get to the end of this talk that there are some considerably questions and a lot of research being done on the next advances in measurement. But just because we have a definition that is not going to change does not mean that the business of metrology is over. Because it's one thing to have a definition, it's another thing to do what we call realize the definition. Realizing the definition means to bring the definition into reality. In other words, I have a definition of the meter, which is how far light travels in a certain length of time. But in order to realize the definition, I need to measure the frequency of the light. I need to make an interferometer that uses that light and then move a mirror a certain distance. I have to account for the phase shift on the mirror if I want to measure the length of an object as opposed to the length of a displacement. And all these things are constantly being improved. So we're certainly not at the end of metrology, even though we may have a definition that doesn't change. We still have plenty of work to do, and there are still going to be new definitions, as we'll see toward the end. So let's continue, and as I said, I'm happy to answer any questions about any part of the talk as we go along. So let's see what's next. Okay, so we have these beautiful definitions, the definition of the meter. And what I'm claiming is that we're now going to bring the same beauty to the kilogram, the ampere, the kelvin, and the mole. So to talk about how we're going to bring this beauty to the kilogram, I'm going to give you a light history of mass. In ancient times, people made artifacts. This is a very common feature of even modern metrology, is artifacts. So here's a set of artifacts from ancient Babylonia, where these various stones were representing certain units of mass. One of these, I forget which one, is called a shekel, a word we often use today. Well, the French revolutionaries decided that they would get rid of these artifacts by using a standard of mass based on the meter. The meter was supposed to be the measure of all things. And so they said, take a liter of water. A liter is just the volume that's contained in a cube that has a side of 1/10 of a meter, 10 centimeters. And the mass of the water that fits into that cube is what we call a kilogram. Now, that's a wonderful idea. It's based on the fundamental properties of a common material, water. It's based on the meter, this new unit of measure that is supposed to be for all people, for all time. But the trouble is, it's not that easy to make a liter of water. The density of the water changes with temperature. The amount of volume of water changes depending upon whether the water sticks to the container, whether the container is hydrophilic or hydrophobic, the nature of the meniscus. So, and it's just difficult to do this with real water. So, guess what? The French revolutionaries made an artifact, and here it is. The thing that I'm holding in this photograph is called the kilogram of the archives. It was and is a cylinder of platinum whose mass was made to be as close as possible to the mass of a liter of water, but much easier to use as a comparison, as a mass comparison, using a balance as compared to putting a container that has a liter of water in it. Much less buoyancy because platinum is one of the densest materials we have. So the buoyancy of the air, which can change, is not as big of a factor as it would be for water. This is a return, in a sense, to the ancient practice based on a good idea of basing the kilogram on the properties of water, but one that wasn't very practical. And so, once again, we have an artifact. Decades later, at the same meter convention that I told you about before in 1875, people made a new kilogram called the International Prototype Kilogram, based on the old kilogram of the archives. This platinum iridium cylinder was made to be as close as possible to the mass of the kilogram of the archives, and it became not just the kilogram for France, but the kilogram for the entire world. This was the last artifact. Up until 2019, this was the definition of the kilogram for the entire world. The kilogram is equal to the mass of the international prototype of the kilogram. Now, I want you to think about this for a moment. We are now in the 21st century. The unit of mass is an artifact, a piece of metal that was made in the 19th century that was based on an object made in the 18th century. This, I think, is scandalous. If someone were to leave a fingerprint on the international prototype of the kilogram, all of us would lose weight, and not in a way that would be very useful. Well, nobody leaves fingerprints on the international prototype kilogram, but it turns out that its mass is changing nevertheless. Here is a plot of the mass of a number of other kilograms, all made at the same time and made to be as identical as possible. These are the kilograms that were distributed to all those countries who signed the Treaty of the Meter in 1875. They got their own version of the kilogram. They were all compared to the international prototype kilogram before being distributed. So everybody knew the mass of their kilogram relative to the definition of the kilogram as being the international prototype kilogram. And these were the measurements that were made, not very frequently, several decades between measurements. But you'll notice that all of the other kilograms are drifting, almost all of them, in the same direction. It doesn't take too much imagination to conclude that the international prototype of the kilogram is probably not constant. But of course, the international prototype of the kilogram cannot change by law. It is by definition and legally always a kilogram, even though it appears that it's probably changing because all the other kilograms are changing relative to it in the same direction. So, again, we have a problem that the kilogram that we have as the definition of mass for the entire world is apparently not stable. And we want to fix this problem. And we want to fix it by using the same beautiful approach that was used for the redefinition of the meter. Now, to define the meter, remember, we defined the speed of light. What constant of nature will we use to redefine the kilogram? Well, to understand that, I want to remind you of what I'm sure is the most famous equation in history, namely that E equals mc squared. And that means that the energy of some object at rest is equal to its mass times the square of the speed of light. where this is called the rest mass of the object. So we specified that the object is at rest. Remember the question about the problematic nature of time? Well, we're specifying that it's at rest relative to us. Okay, so E equals mc squared. Another equation for the energy of a photon, a particle of light, is equal to Planck's constant, h, times the frequency. This was, originated by Max Planck back in 1900, that if you know the frequency of the light, of which this photon is a part, that its energy, the energy of that photon, is proportional to the frequency, and that constant proportionality is Planck's constant. Now, if we just combine these two expressions and solve for the mass, then what we find is the mass is equal to Planck's constant times the frequency divided by the square of the speed of light. So what does this mean? It means if I've got some object, let's imagine an object like a radioactive nucleus, and that radioactive nucleus emits a single photon, a gamma ray, and we measure the frequency of that gamma ray, then because we've defined the speed of light, and because we now intend to define Planck's constant, we now know the mass that was lost by that nucleus when it emitted a photon, a gamma ray. In a sense, we've weighed the photon. Well, we can do this, and people do it, but just not well enough to use this as a redefinition of the kilogram. But there are other ways of doing it. And here is a place where laser cooling also played a role. So here's the idea. Here is an atom, cartoon of an atom. It has two energy levels. These are energy levels that are separated by an optical transition. In other words, I need a laser to excite the atom from the ground state to the excited state. This is usually rubidium, and the laser is a red laser at a wavelength of 780 nanometers. But the point is, you get a laser, you measure its frequency, so you know its wavelength, so you know what the energy of the photon is. You also know the momentum of the photon. It's Planck's constant divided by the wavelength. And you excite the atom using this photon. The atom goes to the excited state, absorbing the energy of the photon, but it also has to absorb the momentum of the photon. So now the atom is moving, and the velocity, just by conservation of momentum, is equal to Planck's constant divided by the mass times the wavelength. And solving for the mass, this tells us that this is the mass of the atom, is equal to Planck's constant divided by the velocity and the wavelength. We've measured the wavelength. We have techniques, which I haven't described to you, that can measure the velocity very, very precisely. We're going to define Planck's constant. We used the definition of c to determine what the wavelength of the light was. So we know everything we need to know in order to get the mass of the atom in kilograms. Now, I want to emphasize how revolutionary this is. We've been measuring for decades, we've been measuring the mass of atoms in what's called atomic mass units. That is, we know what the ratio of the mass of some atom is to the mass of a carbon-12 atom, which is the standard for what we mean by an atomic mass unit. This is not that at all. This is measuring the mass in kilograms. Now, we still, in order to make this useful, we have to multiply up the mass of the atom to something that is the size of a kilogram. And the way that's done is by making a perfect sphere of silicon. Now, why silicon? Because the semiconductor industry has learned how to make perfect crystals of silicon. So this is a perfect crystal of silicon. It's also isotopically pure, so it's all silicon-28, or at least only a part in a million contamination from something other than silicon-28. It's a perfect crystal, and we can measure the lattice constant, the spacing between the atoms, using X-ray interferometry. So we know the spacing between all the silicon atoms. We can measure the size of this spherical object. That means we now know how many silicon atoms are in there. And we can find out what the ratio of our mass of our rubidium atoms is, for example, to the mass of a silicon atom by doing standard comparisons that people have done for decades to measure atomic masses in atomic mass units. So that means we know what the mass of this sphere is. It is not like one of those platinum iridium cylinders where they're made to be equal to the mass of some artifact. This is something that is made from scratch. It's grown out of silicon atoms. This crystal is grown in the way that the semiconductor industry has learned how to make perfect crystals. We've measured the mass of individual silicon atoms, and we know the mass of this object. So anybody could make one. You don't have to have any connection to an artifact. So now we're getting free of the artifact. Now, one of the beauties is this isn't the only way to do it. This gentleman, Brian Kibble, invented what we now call a Kibble balance, where you can realize the definition of a kilogram based on Planck's constant using an electromechanical device. I'm not going to explain it to you because we're running out of time, but we don't have to do it the way I've just described using atoms. We can also do it using macroscopic apparatus. Here's a picture of one of those things. This big thing is called a Kibble balance, and it can measure the kilogram to about a part in 10 to the eighth, which was the degree to which the kilograms were changing from time to time because of, well, we don't know why. We just assume there's some kind of dirt that's getting on the kilograms or coming off the kilograms that's causing their mass to vary by parts in 10 to the eighth. This balance can measure mass that well, and it's going to be stable because it depends upon Planck's constant, not on the cleanliness of the surface of some cylinder made of platinum iridium. And my colleagues at NIST who have worked on measuring this thing take metrology very, very seriously. They have tattooed onto their arms the values of the fundamental constants based on the kinds of measurements that they've been making. And people all over the world have been making such measurements with Kibble balances, with silicon spheres. And when everyone in the world agreed on their measurements, until we redefine Planck's constant, what they're doing is they're measuring Planck's constant. And when everyone agrees on their measurement of Planck's constant to within a few parts in 10 to the eighth, then they redefined the kilogram. Now, there's a final part of the story. And that's, I promised you that there was going to be a redefinition of the ampere. The old definition of the ampere was based on the forces between wires. It was that you put current through two infinitely long straight wires, 1 meter apart, and this would produce a force of 2 times 10 to the minus 7 newtons per meter. The new definition is very quantum. It defines the charge on an electron to be a certain number of coulombs. And now that means that the electron is a certain number of electrons per second. Now, excuse me, sorry. We're not going to count electrons. In fact, we know how to count electrons. We just don't do it well enough yet. We're working on it. So it may be that someday the realization of the ampere will be based on counting electrons. Instead, we use the Josephson effect and the quantum Hall effect, which are based on the electron charge and Planck's constant. We're going to use those quantum effects and defined values of 2a over h and h over e squared. 2a over h gives you hertz per volt. H over E squared gives you ohms. So by using these values, which are now defined, because we've defined both E from the definition of the ampere and H from the definition of the kilogram, that means we know what 2E over H is and what H over E squared are. We can then use those ways of measuring voltage and current to determine an ampere. And that's what we do. Instead of counting electrons, we use the Josephson effect and the quantum Hall effect, which are quantum effects, in order to calibrate the current. And of course, if you put in the numbers, you see that the current is proportional to the charge on the electron, just as you expect. Now, I want to tell you about what I call a dirty little secret about electrical units. For more than a century, since the beginning of the 20th century, there have been, in practice, two different kinds of electrical units in use throughout the world. There has been what we now call the SI unit, although it wasn't called the SI until 1960, but it was based on a definition of the ampere that is in terms of distance and force. And then the ohm and the volt would be defined so that the mechanical and electrical powers are the same. So this was the SI definition. But it's hard to use that definition. It's not very easy at all to measure the force between current-carrying wires. And so people developed an alternate way of measuring electrical units. The legal way, the legal ampere, the legal volt, the legal ohm for a given country were based on standard resistors and standard cells, batteries. So that for example, the United States, the definition of the United States legal ohm was the average of a bunch of resistors that looked like this and that were kept at a constant temperature. And the legal volt was based on a voltage, a defined value for the average of all of these standard batteries, the standard cells. And those legal units were made to be as close as people could make them to the SI units, but these were the ones that were used in everyday practice. And the SI units were from time to time measured, measured against the legal units. So when you measured something with a voltmeter, that voltmeter was calibrated relative to some national standards laboratory, and you were not measuring in SI units, you were measuring in legal units. And almost nobody knew that. I mean, the people who were doing metrology in national laboratories certainly knew it, but the average physicist was typically unaware of the fact that that there were two different sets of units, and you weren't using the actual physics definition, that is the SI definition. Well, the beauty of the current system is that we now, and by the way, I forgot to tell you this, since 1990, all the countries of the world used the same legal units. Up until 1990, they were all using different values because they all had different resistors and different standard cells. But in 1990, they switched to using the Josephson effect and the quantum Hall effect. So at least everybody had the same legal units, but it still wasn't the SI. But now we do, because E and H are now defined in the SI, which means that 2E over H and H over E squared are both exact in the SI, and the legal and SI electrical units are finally the same, but we required a change in the legal units because the old legal units didn't have the latest values of 2E over H and H over E squared. We now have defined values for those, and they're not the ones that were the legal ones before, because those were determined in 1990, and now we're more than 30 years later, so we have better measurements. So I also promised you a new definition of the mole and the Kelvin. It used to be that the mole was the amount of substance, so the number of entities in it, say a mole of water would have a certain number of water molecules that was equal to the number of carbon-12 atoms in 12 grams of carbon-12. The new definition is very atomic. It's simply a number. The new definition of the mole is that that number there, 6.022 times 10 to the 23rd, that number is the number of entities in a mole of anything. And finally, I promised you a new Kelvin, the unit of temperature. It used to be 1 over 273.16 of the triple point of water. Now it's defined by setting the value of Boltzmann's constant, a microscopic constant. Boltzmann's constant times the temperature is equal to the thermokinetic energy of whatever the atomic constituents are. So this is a very atomic way of defining what we mean by temperature, and it opens a new way to realize the Kelvin. We can take a gas and measure the velocity distribution of the atoms in that gas, and from that velocity distribution, which tells us what the thermal kinetic energy is, we can tell what the temperature is. We're not quite there yet, but I feel confident that in the next some years, we will have ways of measuring the temperature that are specifically this very atomic way of measuring the temperature. And so the French Revolution brought us the metric system, with meters as the measurement of length, kilograms as the measure of mass. The meter convention made that international. And on the 20th of May, 2019, which is the anniversary of the signing of the Convention de Metre in 1875, we had this wonderful revolution which brought us freedom from artifacts, and freedom of a double standard for electrical measurements. And so we now have all the units defined by fixing constants of nature. You can keep the International System of Units in your wallet. Here's a copy of a card that you can get that has the values of the defined values of the constants. And so it seems that we have realized the revolutionary dream of a system of units that is good à tous les temps, à tous les peuples, except it seems for time itself, because time is still tied to a specific atom, namely cesium, rather than a fundamental constant. There it is, cesium. Now, clocks are getting better. We now have optical clocks. So instead of a microwave frequency for cesium, about 9 gigahertz, we have frequency standards with atoms like strontium, ytterbium, aluminum ions that are have optical transitions, so several times 10 to the 14 cycles per second. And in part because of the higher frequencies, these optical frequency standards are now operating 2 orders of magnitude better than the microwave frequency standards. These are now good to about a part in 10 to the 18, whereas the microwave standards are only good to about a part in 10 to the 16. But these new optical frequency standards are not yet the definition of the second. We will redefine the second, and we're working on it right now. We don't know what that definition will be. It'll depend upon the development of experimental techniques in laboratories all over the world that are studying these optical transitions. So we're probably going to have a change within a decade. What will it be? And will it be the last one? Well, only time will tell. Thank you very much.
Thank you so much, Professor. Thank you, Professor Phillips, for that incredible insights into the world of quantum mechanics. So we pass to we open now the floor for the last questions.
Okay, so one of these questions is, can a unified theory of gravity and quantum mechanics explain the singularity of black holes and what was before the Big Bang? Well, this is a question that is outside my area of expertise. Uh, so the simple answer is I do not know. There are certainly some people who believe that it doesn't even make any sense to ask about what was before the Big Bang. But there are other people who make speculations about what that would mean. We think of the Big Bang as being a kind of singularity, sort of similar to a black hole, but containing the entire universe. So I'm sorry that I can't give you a good answer to this question. I think that even we don't know the answer to this question now. Will unified theory of gravity and quantum mechanics give us such an answer? Again, I don't know. But I think that it's one of the most intriguing things we have in current physics. And so getting such a unified theory and confirming that, in fact, it does predict something that we didn't know already, so that we can have some confidence that the theory is good, it certainly is an exciting prospect, because it might give us some insight into such fundamental questions as these. Okay, next question. How can we use quantum, I guess this is quantum field theory, QFT, in domains like electrical circuits analysis? Again, this is not part of my expertise, so I don't really know. I know that, well, let's just leave it at that. I simply don't know. I don't know enough about quantum field theory. I think that there are issues that people have raised from time to time about whether macroscopic quantum phenomena like the quantum Hall effect and the Josephson effect, whether these experimental phenomena in fact reflect the real values of 2A over h and h over e squared. And one of the ways in which people have addressed this issue experimentally is to use different materials and compare the Josephson voltage and the quantum Hall resistance of different materials, completely different materials. And so far, everything looks good. At the level at which we are able to make electrical measurements, it looks like it's material independent, and that implies that it is the real value of 2A over h and h over e squared that is reflected in these quantum phenomena. Now, whether quantum field theory can shed light on why that might be so, it wasn't obvious at all that it had to be that way. But it appears to be, and people have come up with arguments, and I could give you an argument for why it has to be that way with the Josephson effect. I'm not sure I can do that for the quantum Hall effect. But that's about all I can say. I simply don't have the expertise to answer that question any better. So next one. Does defining the kilogram via Planck's constant strengthen the unity between quantum theory and classical measurement, or does it simply translate classical quantities into quantum language? Well, again, it seems like it's more of a philosophical question than a physics one. And I think that what it tells, or one of the things it tells us, is that these phenomena, that is Josephson effect and quantum Hall effect, are macroscopic phenomena. We often say, when talking about quantum mechanics, that quantum mechanics is the system of rules that govern what happens at the microscopic, sub-microscopic level of atoms and molecules. And it's true, it is. But things like the Josephson effect are quite macroscopic. I can make two superconductors that I can see with the naked eye and make a junction. between those two uh, those two superconductors. I can make a quantum Hall bar manufactured using lithography that's that's big enough for me to see. So it's not just the sub-microscopic world that's governed by quantum mechanics. So I think that's one of the things this tells us is that quantum mechanics at least sometimes extends into the macroscopic and classical world. Now, people have often speculated whether quantum mechanics somehow will break down when we get to big enough objects. There was recently an experiment done in which microcrystals, nanocrystals, were sent through a diffraction grating, and they behave just like quantum objects. So this was a test to see whether at that level, whether the quantum mechanical behavior of matter would break down, and it did not. But some people speculate that there might be a real boundary between the classical world and the quantum world. And so far, we've seen no such boundary. But the Josephson effect and the quantum Hall effect tell us that at least with respect to those phenomena, we can have something that's quite macroscopic, that's getting much more close to human scale, that is something we can see with our own eyes. And it's still quantum mechanical. So what that tells you, I don't know. But that's as much as I can say about it. Okay, next, bringing the definition to reality, what I called realizing the definition of unit. What are the expected phenomena we can now study better since precise measurements open new doors for scientific applications? I love this because it brings me to one of my favorite new experiments that's being done. Now that we have optical frequency standards that we can measure consistently to parts in 10 to the 18, and probably in the future, that will be parts in 10 to the 19, maybe even parts in 10 to the 20. There doesn't seem to be any natural limit to what we can do. We can do the following kind of experiment, a very fundamental experiment. We can ask, do the fundamental constants of nature change with time? In other words, are the constants constant? Now, the kind of fundamental constant I'm thinking about here is not something like the charge of the electron or Planck's constant or the speed of light. The constant that I'm thinking about here are dimensionless constants, like the fine structure constant. So the fine structure constant is a combination of other constants. It's e squared over 4 pi epsilon naught h bar c, and it's equal to a dimensionless number, approximately 1 over 137. And it's really fundamental in the sense that it describes in a dimensionless way, in a unitless way, how strong electromagnetic interactions are. And there are similar constants for gravity and for the strong force and for the weak force. But the fine structure constant is something we have measured with extremely good accuracy and precision. We know what the fine structure constant is to, I forget what it is, maybe a part in 10 to the 11 or a part in 10 to the 12. But because the fine structure constant comes into the frequency of quantum transition in atoms in different ways depending upon the transition. In other words, a hyperfine transition will depend on the fine structure constant differently from the way in which an optical transition will. And two different kinds of optical transitions will depend upon the fine structure constant in different ways. And if we go to molecules, molecular transitions will depend upon the ratio of the electron mass to the proton mass, which is a dimensionless quantity. They'll depend on that differently from the way, for example, optical transitions in atoms depend on the fine structure constant. So if you get two atoms that have a different dependence of their fundamental transitions on the fine structure constant and compare those two frequencies corresponding to those transitions to each other. In other words, let's say you take strontium and terbium. I don't remember if that's a good choice, but let's say you take strontium and terbium, both of which have optical transitions that can be measured very precisely, and you compare them. You can compare them to a part in 10 to the 18 over a period of years. So we now know that the fine structure constant doesn't change by a part in 10 to the 18th in a year, even though we only know what it is to a part in 10 to the 11 or a part in 10 to the 12. So this is a really fundamental piece of information that that these even more fundamental constants of nature are not changing, at least as far as we can measure. People have speculated that they do, and now we know that they don't, at least not now. Maybe they changed early, right after the Big Bang, but at least right now they are not changing at the level of a part in 10 to the 18. So this is an example of the kind of new physics that we can do because of the fact that we've done better metrology. Okay, the next question says, looking back at your early career, what conceptual shift most transformed your way of thinking as a physicist? Well, let's go back really far to when I was a young student. One of the things that I remember very clearly changing my perspective was the understanding of the way in which calculus allowed me to understand physics. So when I was first studying physics, one of the things you study is circular motion, and you know that if something's going around in a circle, that the acceleration is toward the center. This is why, for example, orbits of planets are nearly circular because there's a force on the planet to the sun. I mean, of course, it's exactly elliptical, but if you have a circular orbit, then the acceleration is toward the center, and that corresponds to the force between the sun and the planet. And I remember writing down the equation, the parametric equation for a circle, parametrized on time, and then taking the second derivative of that and seeing that the second derivative of the parametric equation for the circle was pointing toward the center. And I thought, wow, this calculus stuff is really great. And calculus has become, even though I don't use it the way a theorist would, I'm an experimentalist, but calculus has become the way I think about the way the universe works, that things move the way they do because they're subject to a force. And Newton's law says that the acceleration is equal to the force divided by the mass. And the acceleration is the second derivative of the position. So it's just calculus is the thing that will tell me how things work. And someone asked the question earlier about mathematics. I think that if you're going to be a physicist, then you have to understand calculus because it's the way physics works. It's the way the world works. And I remember Richard Feynman, one of the iconic physicists of the 20th century, gave a series of lectures, and I recommend them highly. They're called The Character of Physical Law. And he gave a whole series of lectures, and one of them was about gravitation. And he said that people knew that the planets were going around the sun, but they didn't really understand, or they knew at least that the planets were moving, but they didn't really understand why. And they sort of imagined that there were angels that were pushing the planets around. And he said, they almost had it right. He said, the angels are pushing in toward the sun. What he meant was that we don't really have any better understanding of how gravity works than, or what the origin of gravity is, than ancient people might have imagined that angels are responsible for the forces on things, but that now we know those angels are pointing in, and that's what physics and calculus gives us. And I think it was a wonderful perspective that Feynman gave, that we still don't understand things at a really fundamental level. Well, we understand some of the details about how they work. So now the angels that are operating on the planets are pointing in toward the sun instead of driving them around on their orbits. Well,
Okay, I think this is the last question. We are really honored by your presence here today. At this time, please join me once more in thanking Professor Phillips. Thank you, Phillips, for being here with us today.
Thank you. It's been a pleasure for me.
Thank you so much.
And I very much enjoyed all your questions.
Of course, thank you so much for being here.
Well, thank you. And we'll be in touch again, I'm